Going live. There we are. Welcome back. Looks like out of 20 something people in the class, there's only 3 people present right now. That's okay. That doesn't hurt my self esteem in the least. It's not like I'm going to sit here and cry for a little bit after the class is over. I don't know. Maybe I'll do a little bit of both. We'll see. So I'll stall for a little bit and give you an idea as to what today is going to hold and what next week is going to hold. Because I need everyone to be on the same page with this thing. There are some important dates coming up that I'm going to remind you of as time is moving forward in these crazy times. Anyway, here's where we're at. First, for you guys, today's lesson is going to be some more polynomial practice, a variety of problems that it's going to run the gambit of a lot of different things over the course of this chapter. And it's a twofold thing that I want to do this for. Number one, it's important for you to be able to recognize what is expected of you when you are solving problems like this. Number two, we do have next week, I'm going to be assigning you a major assessment in regards to this chapter. So I want everyone to be ready for that, of course. Now, next week, I want to knock out that major assessment. It'd be fantastic. We're all going to high five at a social distance. Good, fine, and dandy. 2 weeks from today, progress reports are due. Now, this is going to be a little strange, obviously, considering the fact that it feels like the marking period just started, but each marking period is roughly 9 weeks long. And, well, that means 4.5 weeks between, progress reports. So that's where we're at. 2 weeks from today, progress reports are due. Now, there's an assignment that you have due for me Monday, a graphing assignment that is due Monday. Make sure you're checking Google Classroom. And then sometime mid next week, I am going to be assigning that major assessment. Because, 2 weeks from today, progress reports. And I'm going to have all of that stuff submitted. Fun. Oh, my fun. You guys are weird. Anyway, back to this. So, then, of course, we have the week of the 21st, which is what I have to fill you guys in on again, just so you're aware of it. The week of the 21st, Monday, Tuesday, Wednesday, that's a short week. That shortened week, you guys are going to have to complete benchmarks. Yay. No, I will not leave you alone. Anyway, where was I? Yeah. So number one, you have an assignment due Monday. Number two, I'm going to be giving you a major in the middle of next week. Number three, 2 weeks from today, progress reports. Number four, the week of the 21st, we're going to be knocking out benchmarks. And then it's Christmas break. And then when we get back from Christmas break, there's like a week or so, and then we're going to begin reviewing for midterms. Oh, man, it's going to be one thing after the other. I know. Fun. And in between all of that, we have to deal with COVID and quarantining, and who knows what the heck is going to happen. Maybe I'll see you next week. We'll see. Anyway, as I said for today I would like to spend getting some practice with polynomial problems. And it's going to be a variety of things. Sometimes we'll be graphing, sometimes we'll be factoring, sometimes we'll be solving. It depends on what the problem is asking for. And I'm going to review all of that stuff with you guys here today. So, if you do not already have them out, I'm going to need those notebooks out and open. Just adjusting my screen before I walk over there. Just so you guys know, even though I'm not by the computer, I still will be able to adjust this silly thing. There we have in the chat, because I will have in a few moments, I will have the chat open on my phone by my desk. So let me open Desmos, because I will need Desmos a little bit later. There it is. And there No, not that thing. Go to Desmos. There we go. Good. So let's start with a little bit of this. I'm going to title this Polynomial Practice. And today is the 4th. Now, hopefully, today is going to bring together a lot of different aspects of this process that we have been dealing with over the course of the past several weeks. That is the end goal for this kind of thing. I don't even know what you guys are doing in the chat right now, but I digress. So let's start with something like this. F of x equals x cubed minus x squared minus 4x plus 4. To kind of get started with this, process, let's just start with a problem where we have to do everything. We're going to do everything with this problem. We're going to factor this problem. We're going to solve this problem. We're going to graph this problem. We're going to describe the end behavior of this problem. We're going to do everything in our power to try and get this thing done. And along the way, I am going to be describing various attributes of this polynomial that we know based on the definitions that we have been collecting over the past several weeks. So first and foremost, I'm looking at this polynomial. How do I know it's a polynomial? A polynomial is an equation where all of the exponents are positive whole numbers. And in this case, you see an exponent of 3, 2, and technically that's an exponent of 1 right there. But I digress. What? I don't know what's going on in the chat. Maybe I should just block all of them. Anyway, I don't know. Now, the degree of that polynomial is 3. It is a third degree polynomial. How do I know it's a third degree polynomial? Well, I know it's a third degree polynomial because number 1, it's a polynomial. Number 2, the largest exponent is a 3. It doesn't matter what order these things are written in. Whatever the largest exponent is the degree of the polynomial. What is the leading coefficient? The leading coefficient of this particular problem is a 1, a positive 1. Well, how do you know that? I know it's a positive 1 because the number, the coefficient, in front of the variable with the largest exponent is a 1. Again, it doesn't matter what order these things are written in. I would be looking for the degree, and whatever number, the coefficient that is in front of that variable with the degree is the leading coefficient. All of that tells me a lot. First of all, I'm going to write this to the side before I actually begin this problem. The degree is 3. The leading coefficient is 1. This tells me that I have an end behavior that resembles that picture that I just drew. Now, I'm not going to leave my end behavior like that. I am going to use the notation eventually at the end. But that is what the graph should eventually resemble in terms of end behavior. It is an odd degree, which means that the end behavior goes in opposite directions. Opposite directions. You know, someone once asked me, Mr. Markey, you have a pun for opposite directions, but will you ever come up with a pun for an even degree? And I told them, I don't know. Eventually. Nailed it. I'm assuming at this point that everyone is just standing up at their computers and clapping and applauding. And I accept your adulation just because that was a classic joke. Anyway, back to this. Eventually. Okay. My cord keeps getting tangled. That's weird. Anyway, so I'm looking at this problem, and I got to figure out, okay, how am I going to start this thing? How am I going to begin it? I got to do everything with this. I got to factor it. I got to solve it. I got to graph it. I got to start somewhere. And where you start is the graph. You got to look at the graph of this particular problem. Now, Madison, I'll tell you, actually, I am so used to telling jokes in front of a class that is barely existing that having no one in the room makes this all the more fun for me. Also, I have been, by the way, I'm going to bring up Desmos while I'm telling you this. I have been live streaming a lot at home in the past many months. And as a result, I'm used to reacting to people online who have basically no voice, but it's really just me reacting to their words. And I find it hilarious. You see, she gets it. Serenity gets it. You know what? You get a sticker. I've said it. You get a sticker. Anyway, back to this. So what I did was I typed the equation into Desmos just to get a visual as to what's going on here. Because when you are trying to factor this, when you are trying to solve it, the best course of action is to first look at the graph. If you look at the graph, you can visibly identify a lot of different pieces of information. First of all, we can visibly identify some x-intercepts, which is going to help us begin the factoring solving process. We can even identify turns and where these turns actually occur. Remember, a turn is a change in vertical direction. Up to down, down to up. Now, let me talk about these definitions. In the past few weeks, we've been talking about the definitions of a degree of a polynomial. What does the degree of the polynomial tell us? This is a third degree polynomial. What that means for us, well, according to the definition, if the degree is 3, that must mean it has at least 3 real solutions. That is one of the definitions that we have written down. It has at least 3 real solutions. Now, looking at it, it actually does have 3 solutions, so we're good there. I say at least, I apologize, at most. What we wrote down in our notes was at most. I got to think at most because 3 or less. It's got to be at most. I misspoke before. But if we wanted to get a little bit more specific, if you included repeats and complex solutions, then it should have exactly 3. But it looks like it does have 3 real, so we're good there. The other definition that we had was about turning points. If the degree is 3, then it will have at most, I said it right that time, at most n minus 1 turning points, which means if the degree is 3, then it should have at most 2 turning points. And this one does. It has exactly 2. It doesn't have to have 2. It could have none. But this thing has a turning point up here and has a turning point down here. It has the 2 turning points. These are just different characteristics that you can identify solely based on the equation by being able to identify the degree of the polynomial. And now looking at this thing, it does fit that criteria. Okay. Visibly, I can see +2, +1, and -2 as the zeros of the function. Now, I visibly identify that on the graph. I could visibly identify that on my graphing calculator, but I still need to show the work in order to prove that. This is what you are eventually going to do on that major assessment next week. This is what you are going to do on that homework that I have due Monday for you guys. Make sure you're paying attention to the assignments in Google Classroom. But if I'm going to begin this process, okay, I visibly identified those zeros. Now let me go about trying to prove it. And if I am going to go about trying to prove it, let's start with some synthetic division. 1, -1, -4, +4. Those are the coefficients that I get directly from the equation. Okay. Where do I get the number from out here? Well, I visibly identified those numbers on the graph. I visibly identified a +2. Okay. Let's prove it. If we're correct, there should be a 0 down here in the bottom right. All right. 1 plus nothing is 1. Multiply. Add. Multiply. Oh, that's weird. Multiply. Add. Multiply. Add. Nailed it. What we have just done is we have proven that 2 is a 0 of the function. Now, that's not the factor. That's not the factor. A factor is a different thing, but that is definitely the 0 or one of the zeros of the function. Now, I'll write this all out later when we identify our factors and our zeros, but let's see what we have. Because now that we've done the synthetic division, now that we have divided out that particular 0, we have an equation left over. You start with a third-degree polynomial. You divide out one of the zeros, one of the factors, technically. This is the factor x minus 2. We have divided it out. And when you divide a factor out of a third-degree polynomial, what is left over is a second-degree polynomial. This is your remainder, your constant, your x squared. You have a quadratic left over. And when you have a quadratic left over, you have options. You have options. And these options for having a quadratic, well, number one, you could continue with synthetic division if you had more zeros to divide out, okay? Number two, you could factor, which is what I'm about to do in a few moments. Number three, you could do the quad formula to get the remaining solutions. Okay, honestly, you could do any of that stuff. What I'm going to do is option 2. Doesn't matter which one I do, but I'm going to do option 2 here. And option 2 is writing out this equation as a quadratic and factoring it. So, my microphone. Stay there. There we go. Good. Remainder constant x squared. This is a 1x squared plus 1x minus 2. Which factors, if you do the Tucker method of factoring or whatever method of factoring that you have to get that thing done, you can factor that into x plus 2, x minus 1. You have to know how to do that. Knowing those factors, I'm ready to answer the first part of this problem. Number one, factoring the problem. What are my factors? Well, I got these two factors from the quadratic. I got these two factors directly from the quadratic. There is a third factor, though. That third factor comes from this number. Now, I'm not going to write a 2, a positive 2, I should say. I'm not just going to write it as that. I'm not going to write x plus 2 again. This becomes x minus 2. This fits the definition of, well, if f of k is equal to 0, then x minus k is a factor. That is the definition that I gave you, I don't know how many weeks ago. If f of k, in this case 2, is a 0, then x minus k, or minus 2, is a factor. Those are my factors. So what about my zeros? What about my solutions? What about my roots? What about my x-intercepts? Well, in order, -2, +1, and we proved this using the synthetic division, +2. Those are my zeros. What you have to do on each of these problems depends on what the question is actually asking of you. The question may ask any number of things. It may ask any number of things. For this particular problem, I wanted to do it all. I wanted to factor it. I wanted to solve it. And of course, I want to graph this thing as well. So let's begin the process of getting that done. In order to graph it, it would be important to have the zeros of the function, to know exactly what this thing generally looks like before I get to be a little bit more detailed. Now, of course, you have your graphing calculators. Good for you. Let me get my calculator ready. Good. Let me zoom in. You have your graphing calculators. I have my graphing calculator. I'll focus it in a moment. There it is. I'm in the y equals key. In the y equals key, I'm going to type in my equation. This is what you would do in order to get what you're about to do. You type your equation into the y equals key. You can graph it if you want. That's fine. It'll show the same picture it did on Desmos. Oh, happy day. But that's not what I'm interested in. What I'm interested in is a table of values. And to get that table of values, you got to hit second graph. And it takes you to a proper table of values. Now, I'm going to write down a bunch of these ordered pairs. I am. But where to start? Well, let me scroll back a little bit. Oh, there we go. Interesting. Okay. Look at this compared to the end behavior sketch that I did right here. Look at this end behavior sketch that I did. To the left, this thing is going down forever. To the left, it's going down forever. If I keep going to the left for my x values, it gets larger and larger and larger negative numbers. That makes sense. That's following the end behavior. If it's following the end behavior, then I know that I'm on the right track. What about in the other direction? The other direction, according to the little sketch, it should be going up to positive infinity. And look what these numbers are doing when you move to the right on the table of values. There's a little glare there. I know, I apologize, but you have your own graphing calculator to see it as well. But these y values are getting larger and larger and larger because the end behavior is going higher and higher and higher. Now, like I said, I'm not going to write down all of these numbers, but I am going to write down the ones that I need. I'm going to write down the following. Let's see here. Zoom out. There we go. I'm going to write down the following ordered pairs. And this is directly from the table of values. I'm going to start with -3, -20. Now, I'm not going to plot -3, -20. -20 seems way too far down. But it's the first number on the far left that I would not plot. Usually I have that as a reference, so I know what direction I'm going to be going when I'm drawing that end behavior. Then -2, 0. Then -1, 6. Then 0, 4. 0, 4 is the y-intercept for reference. Then 1, 0, 2, 0. 3, 10, which I am going to be plotting that one. And 4, 36, which I am not going to be plotting that one. Now, all of these numbers make absolute sense with what we've done so far. We have identified those 3 zeros. We knew that there were 3 of them, and we found all 3 of them. Yay, good for us. It matches the end behavior, going to the right up, going to the left down. Yeah, this looks pretty solid. I'm ready to graph this sucker. All right. Let's see what happens. Ha-ha! Of course, I'm going to draw this thing by hand. I'm going to be expecting accuracy when you are the ones drawing this by hand. On that major assessment, there is going to be a component where you have to do stuff on your own. And I'm not just going to accept some random sketch that you threw. Oh, this is what it looked like. So, no. Accuracy. Let's see. -2, 0. There it is right there. -1, 6, which is up here. Good for me. 0, 4. Haha. 1, 0. 2, 0. And 3, 10. Oops. That was an accident. We'll cross that out. Goodness. I wish I had. Do I have whiteout? I think I have whiteout. I thought I had whiteout. Oh, I do have liquid paper. Is that what it is? Hope it hasn't dried out. Whew. This thing is old. Let's see if I can get that. Look at that. That was pretty solid. Oh, it's funny. I've had this thing for I don't know how many years. Oh, and I've never used it. Anyway, until now. But now it's gone. Now, drawing this thing, you're not just going to connect the dots and hope for the best. This thing has to be a smooth curve. You're going to be going through the points left to right. So smooth curve left to right. Hitting those proper points. Coming back down. Now, right here, you would not just make a horizontal line. That horizontal line is not existing because we know that this thing is going to dip down and come back up. Hey, how far are we supposed to dip down? I don't know. Depends. You could base it on what the graph looks like. And this thing's going to fire up. Now, you need to have this left end as well because that's what that end behavior did. That end behavior went down like that. Solid. This is exactly what this thing does. See, -3 would be at -20 all the way down here. Yep. +4 would be at +36 all the way up there. Yep. I'm not plotting those, but I know that they're there. Fantastic. This is what it looks like. What it resembles. Now I need to write the notation for end behavior. As x goes to the right. Notice how I wrote that. As x approaches infinity, as x goes to the right, the function goes up. That's what that thing does. Phenomenal. As x goes to the left, as x approaches negative infinity, the function goes down, also approaching negative infinity. Remember, there are 4 types of end behavior. That's the one needed for this. You would translate it as x goes to the right, as x goes to the left, things of that nature. What does the function do? F of x goes up or f of x goes down? Phenomenal. Okay. Let's see what's next. I have various examples that I would like to do. Is that dry? Oh, wow, that dried pretty quickly. That was pretty solid. I got to use that more often. Anyway, here's an example that we are not going to graph, but we are going to look at the graph. Here's an example that we are not actually going to end up graphing, but we are going to look at the graph in order to identify some key things. So first and foremost, I'm given this problem. And the directions that may be given to me on this particular problem would be, hey, factor this thing completely. And find all of the solutions. Now, let me emphasize what I just said. I'm asking for you to factor completely, and I'm asking for you to find all of the solutions, not just the real ones. Now, according to the definitions that we have been given, this is a fourth degree polynomial. This is a fourth degree polynomial, which means that at most it would have 4 real solutions. But according to that other definition, it would have exactly 4 solutions if you include repeats and complex. Now, where the heck do you start with this thing? Well, we're going to look at the graph in a moment, but let me point out something to you about this particular equation. It is a fourth degree polynomial. Sparky, how do you know that? Because the largest exponent is a 4. That's the largest exponent. Doesn't matter what order you write them in. The largest exponent's a 4. It's a fourth degree polynomial. Also, it does not have an x cubed. And it does not have an x to the first. Those are things that you have to keep in mind when you are going throughout the course of this problem, because it will affect the way that we do things. Now, according to this, we need to find all of the solutions, which means in the end, you're going to actually give me exactly 4 solutions made up of the real solutions, repeated solutions, and complex solutions. But let's just see what the graph looks like. If I were to look at this graph, and don't panic when I do this. Let me type it in correctly, first of all. I haven't typed it in yet. Here we go. X to the 4th minus 5x squared minus 36. Okay. Here we go. Don't panic. Zoom, zoom. Did you? What? It's just like 2 lines. Where the heck is the rest of it? Oh, that's weird. It's okay that we don't see it all. It's okay that we don't see it all. Because I didn't ask you to graph this thing. Instead, what I had asked you was to find all the solutions. And where we typically start is by looking at the graph and seeing if we can identify any real solutions. And what I'm seeing up here, hopefully you can see it as well, is that I can visibly identify 2 of the solutions. There's one over here at +3. There's one over here at -3. That's where I'm going to start. That's where I'm going to start with this process. I'm going to start at +3. I'm going to, then go to -3. Let me take a peek at Desmos real quick. I want to take a peek at Desmos just to see what the heck is going on here. Desmos. X to the 4th minus 5x squared minus 36. All right. There's the 2 lines that we talked about. But watch this. Oops. Watch what happens at the bottom right here. What the heck? Visibly, this thing is terrible. But I wanted to point something out to you. It looks like the bottom of a tooth, by the way. It looks like the bottom of like an incisor or some junk like that. But look at the turning points. It has a turning point here. It has a turning point here. It has a turning point here. It has 3 turning points. A fourth degree polynomial has at most 3 turning points. And that's exactly what it has. Nice. It doesn't have to have 3 turning points. It could have less than. It has at most 3. This thing just so happened to have 3. That's such a weird looking graph, but that's exactly what it does. It fits the definition. Okay. Let's go back to here. Zooming back out. So where do I start? On the graph, I was able to visibly identify 2 zeros. 3 and -3. It should have 2 more. I don't know what they are. That's okay. I'm going to start with a 3 right there. The numbers that I'm putting on the inside are these. You need to recognize, as I stated earlier, the x cubed is missing. You need to have a placeholder. The x is missing. You need to have a placeholder in order. You need to have them in order. All right, let's begin this. 1 plus nothing is 1. Multiply, add, multiply, add, multiply, add, multiply, add. Okay. I knew it was going to work. It's just we had to prove it. Here's the other thing that I want you to recognize. Look where I'm pointing right now. Remainder, constant, x squared, x cubed. It's a 4th degree polynomial that we have now whittled down to a 3rd degree polynomial. I need to get it to a quadratic, and then I have options. So I'm going to need to do another synthetic division. I don't include the remainder. I'm going to need to do another synthetic division with another 0 that I was able to visibly identify. In this case, -3. All right, let's do it again. It should work. 1 plus nothing, multiply, add, multiply, add, multiply, add. Nailed it. But again, look what you have left over. Look where I'm pointing. I'm pointing at the bottom of the screen right now. Remainder, constant, x, which, yes, that is a 0x, x squared. Okay. Now, what's really interesting about that is an x squared plus 4. That is the resulting quadratic. Now, what's really interesting about that resulting quadratic is it is not factorable. It's not factorable. You can try all day long. It's not going to be factored. There are no such two numbers that multiply to 4 and add up to 0. You can't do it. So that actually is the resulting factor. The first question that I had asked was, hey, factor this thing. Okay, factor this thing. X squared plus 4 is a factor. Look where I'm pointing. This results in the factor x minus 3. And look where I'm pointing. That number results in the factor x plus 3. Oh no, I drew on my table. Whatever. These are my factors. If you were to multiply them back together, you would end up with that original original quartic. Now notice what I'm writing here. Real solutions. I only saw 2 of them. I only saw 2 real solutions. I saw positive 3 and I saw negative 3. Yes, those are indeed your real solutions. But they are not all of your solutions. They are definitely not all of your solutions. Because according to the definition, it's a 4th degree polynomial, so it should have exactly 4 solutions if you include repeats and complex. That resulting x squared plus 4. Look at my graphing calculator right here. That resulting x squared plus 4. Look at the graph of this equation. It's a quadratic. How many x-intercepts does it have? It doesn't have any x-intercepts, but it does have two more solutions hidden inside. It has two complex solutions, two unfortunately named imaginary solutions. How do I find them? Well, remember what I told you. You have options. You have three options. Option number one, can you continue with synthetic division? No, you can't. You can't continue with synthetic division because you don't have any more zeros to divide out of it. Okay? Can I factor it? No, we just talked about that. You actually cannot factor it. The only option that you have left is the quadratic formula. That is the only option you have left. So let's do it. Your discriminant, b squared minus 4ac, would be the following. Now, if you remember our conversations on calculating the discriminant, if your discriminant was positive, then you would have two real solutions out of it. If your discriminant was 0, then you would only have one, which actually is a repeated 0. And if your discriminant was negative, as we have in front of you right now, then you would have two complex, or the unfortunately named imaginary. That's what this thing does. Ha-ha. Now, I'm going to have to continue with the quadratic formula. I only have the discriminant, but I wanted to calculate the discriminant separately, keeping in mind that, again, it's a 0x, so your b value was 0. So it would be negative b plus or minus the square root of the discriminant. The whole thing is over 2 times a. Oh, but Mr. Markey, you're not allowed to take the square root of a negative. I know. You're not allowed to take the square root of a negative. Because what happens when you, zooming in, what happens when you try to take the square root of a negative? Enter non-real answer. But what I've showed you is that if you hit mode and go down to the word real and change it to a plus bi, all of a sudden, you can do that calculation again, and you get 4i. If you remember what we did when we covered complex solutions and complex problems, is that you would get an I if you took the square root of negative 1. Well, that negative underneath the square root comes out as an I. And if that negative comes out as an I, then what is the square root of 16? Well, it's 4. 4i. That is what happens with that problem. You can break up the negative 16 to be the square root of 16 and the square root of negative 1. The square root of 16 becomes a 4. The square root of negative 1 becomes an I. I has been on that calculator this entire time. Most of you just did not know that. So, I'm continuing with this calculation. This becomes plus or minus 4i over 2, which reduces to plus or minus 2i. Which means my solutions, notice I did not say real, but I said just flat out solutions, which according to our definition, if the degree is 4, then we should have exactly 4 solutions, are 3, negative 3, 2i, and negative 2i. They are our 4 solutions. It's really messed up what this thing is asking you to do. It's phenomenal. Phenomenal. Okay. I have 2 more problems that I would like to try with you. Just 2 more. One of them is going to be pretty straightforward. The other one's going to be a little bit more of a doozy. I love doozies. Again, the purpose of today was polynomial practice. What do I do depending on what the question is asking? Example. Divide. X cubed minus 2x squared minus 9 divided by x minus 3. The question just wants to know what's the result. What do you get when you divide these two polynomials? Ugh, I don't know. Can I look at the graph? All right, you can look at the graph if you want. Hold on, let's take a look. X cubed minus 2x squared minus 9. I'm not going to type in the x minus 3 right now. I just want to look at the graph real quick. I'll put in the graph in a moment. It may help if I put the parentheses in as well. Ha! There are your parentheses. Oh, I lost the square. It was 2x squared. There we go. Minus 9. It's missing the x term. Let's graph it and see what happens. Well, that's gross looking. Down at the bottom, it looks like it's doing a couple of turns down there. And up here, it only looks like it crosses the x-axis once. Huh. It's very strange. I mean, I think it crosses at positive 3. I think it does. Technically, you didn't have to look at the graph because all it wanted you to do was divide. And if what you had to do was divide 1, negative 2, 0, negative 9, these are the coefficients in order. It's missing the x term, so I got to put a 0 in for the x term. I'm dividing by x minus 3. I don't put a negative 3 in front of the bar. I'm not putting a negative 3 there. If you're dividing by x minus 3, you put a positive 3 in front of the bar because that's the 0 of that factor. 1 plus nothing is 1. Multiply, add, multiply, add, multiply, add. I got a remainder of 0. That wasn't a guarantee. It wasn't a guarantee that I would get a remainder of 0. It wouldn't. I mean, I don't know. I could have gotten anything. All it wanted me to do was divide. It didn't want me to find the zeros. It didn't want me to solve anything. It didn't even want me to graph it. It just wanted me to divide the two. So what do I write as an answer? Your remainder is 0. Constant, x squared. This is a 1x squared plus x plus 3 as the result of the division. That's the result of the division. That's all the problem wanted me to do? Yeah. That's all the problem wanted you to do. See, the thing is, it depends on what the question is asking. On the previous problem, it wanted me to just find all the solutions and factor it. Well, I was able to factor it, yeah, and I had to write all of those terms out. This problem didn't want me to factor. This problem didn't want me to graph. This problem didn't want me to solve. It just wanted me to divide them and give the result. Done. Depending on what it's asking, guys. Depends on what it is asking. Last problem of the day. Last problem of the day. There it is. Example. Solve. 5x cubed equals 30x minus 25x squared. Oh, solve. What is that? What solve? What do you mean solve? Solve. Get x by itself. Figure out what x is. All right, well, what do I do? How do I start? Well, let's just take an inventory of what we have. What we have, they're telling us to solve, and there's an equation. They're not asking you to graph anything, although we will take a look at some kind of graph in a little bit. They're not asking you to factor. They're asking for you to have x by itself. Okay. What do I do? Well, notice I have an equation. And notice that that equation is not equal to 0. Typically speaking, if you're going to solve for x and you have multiple x's floating throughout the problem, like an x cubed, then an x squared, and an x, it's a good idea if you get one side equal to 0. Ultimately, I would like to try and factor this thing, see if I can't get the zeros out of that. Sometimes you can, sometimes you can't. But it may be a good idea to get one side equal to 0. So let's do that. I'm going to add the 25x squared and subtract the 30x from both sides. Okay, good start. All right. What do you do now? Well, this is technically not a quadratic, it's a cubic. But if you were going to solve, maybe it would be a good idea to try and factor. The first step of factoring is typically those magical 3 letters, G, C, F, greatest common factor. You could take out a 5. It might help. It might make things a little bit easier. You could also take out an X because they all have X in common. I'm going to pretend like I didn't know any of that. I'm going to pretend like, oh, I don't know what to do. Okay. If you don't know what to do, perhaps it would be a good idea to look at the graph. Now, again, we're not being asked to graph this thing, and I'm not going to expect you to graph this thing. But it is a good idea to look at the graph, not to graph it, but to see the zeros of the function. This is a third-degree polynomial, which means at most it could have 3 x-intercepts. Let's just take a look at the graph and see what happens. By the way, another reason for getting it equal to 0, if you get it equal to 0, then visibly the x-intercepts would be the solutions you're looking for. Let's graph it. Ooh. That's gross. That's really gross. What the heck even is that? I don't know. It doesn't matter. Doesn't matter. Can you visibly identify any x-intercepts? That's the point. If you can visibly identify any x-intercepts, you can get this problem moving. Right here. It looks like -6. Spoiler, it is -6. That's a good place for me to start. Let's start there. I don't know anything else about this problem other than maybe it crosses by -6. Let's give it a shot. Somebody asked me yesterday, Miss Markey, where'd you get the -6? From the graph. All right. Let's put in the numbers. 5, 25, -30. Wait a minute. It's missing the constant. If it's missing a term, you have to put in a placeholder. You have to. If it's missing a term in order, you have to put in a placeholder. It's missing the constant. 5 plus nothing, multiply, add, multiply, add, multiply, add. Okay. All the rules remain the same. Remainder, constant, x squared. All the rules remain the same. Okay. So that must mean I have a 5x squared minus 5x? Yes, you do. All right. Well, what do I do from here? I don't know. It's a quadratic, so now you have options. You can continue with synthetic, or you can try to factor it. I'm going to try and factor it. I'm going to take out a GCF of 5x now. I could have done this earlier, but I decided to do it now just for funsies. I factored it. It's no longer a quadratic. I have it factored. I'm going to set these factors equal to 0, and I'm going to solve. I get a 0 of, well, 0. Let me repeat that. I get a ZERO of the numeric value 0. I get a 0 of 0. Weird. I get a 0 of 1. And I proved it using the synthetic division, but I proved that 0 of -6. I'm going to go back to the graph in a moment. But that weird looking thing that we saw on the graph does show all 3 of those solutions. It just looks terrible. It just looks horrendous. But that's okay. Let me zoom in right here. Here's that terrible looking graph. There's -6 blinking in all of its glory as my x-intercept. There's +1 blinking in all of its splendor. And bringing up the rear, this graph goes through the origin. It goes through 0, 0. That's nuts. Just as nuts, this thing. I know. But I knew it had 3 solutions because of the degree of the polynomial. Okay. You guys have a graphing assignment due for me on Monday. Next week, I am going to be assigning a major assessment for the chapter. 2 weeks from now, progress reports. And the week of the 21st, benchmarks. It's going to be fun. Anyway, there's my time because the bell's going to ring. Nailed it. But if you guys have any questions, make sure you are contacting me, emailing me. Everyone have a wonderful weekend. Take the stuff from underneath your desks, and maybe I will see, well, the tops of your faces because the bottoms will be covered next week. All right. See ya.